bring it on. Gonna get that A, then we're gone. Revising with Mr. Marsh. Yeah! Revising with Mr. Marsh. Woo! Got that chemistry swagger. Nothing's gonna drag us after Mr. Marsh. Yeah! Mr. Marsh. Woo! We're ready for the test now.
Okay, science nerds, we're doing it. It's the Chemistry CT. It is Year 9 chemistry paper, atomic structure, periodic table, ionic and covalent bonding. How real. That's great. Let's have a little look what we got. We are 45 minutes and 45 marks. So a mark a minute, pretty standard for these things. You may use a calculator, show your workings, and you get a periodic table. It's on the back. Here, look, a periodic table. Hey, that's very happy. Right, let's look at question number 1. Let's get on with it. So you should be correcting as you go. Complete the table to show the relative mass of a neutron and an electron. Relative mass, not charge, mass. Proton has a mass of 1. Clue. Neutron has a mass of 1. Electron, not 0. But you could give the fraction 1/2000th-ish. Almost 0. Negligible, right? Something that indicates that it's not 0, but is very, very small. The actual figure they give in the mark scheme is 1,837ths of the mass relative to a proton or neutron, but we're talking tiny numbers. They will give you anything between these two numbers, and that would be absolutely fine. So 1/5000ths upwards are allowed. So anything but not 0, but anything that says that you know it's almost 0. There we go. Complete the sentence by putting a cross in the box. An atom has no overall charge because it contains. An atom has no overall charge. Electrons are negative, protons are positive, same number of electrons and protons. Give yourself a mark. The atomic structure of lithium, the atomic number of lithium is 3. The mass number of an atom of lithium is 7. State the name and number of each of the particles in the nucleus of this atom. So we are looking at the nucleus. Now, luckily in the mark scheme, I think it said ignore any reference to electrons, but I don't think it liked it. We're looking at the nucleus, and if you didn't show the nucleus, then you didn't show the nucleons, and you start talking about electrons going around in shells on the outside, it shows you didn't understand the question. The question's asked about the nucleus, the stuff in the middle. So we've got 3 protons, because the atomic number is 3. We've got the mass number of 7, and so 7 minus 3 is 4. So we know that we have 3 protons, and therefore we have 7 minus 3 equals 4 neutrons. Do you see? So 7 and 3 is the answer. Write that down. Easy to work out. Easy to work out. Beryllium, Be, has an atomic number of 4. Yeah. Complete the sentence by putting a cross in the box next to the answer from the position of the periodic table. Beryllium is likely to be a metal, halogen, compound, periodic table of elements being a compound, gas at room temperature. Okay, let's find it. Oh, there it is, beryllium, left-hand side. It's on the left, so it's on the left-hand side. What do we know about the left-hand side of the periodic table? There's that step. Anything to the left of it are metals. It's in the left-hand side, so it's a metal, isn't it? Yeah. Give yourself a tick. If you didn't get it, correct it. Give the symbol of an atom of another element in the same period of the periodic table as beryllium. Remember, groups go down and periods go across. So I've got a lovely video of that in YouTube. I should link it in the description. But yes, groups go down and periods go across. I'm totally going to link that in the description. I should remind myself. If you're watching on YouTube, hi, drop a comment, a like, subscribe. So let's go across. Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. Anything from that period, and they allowed anything from that period. So I would give lithium because it's the first one, but you could equally say boron, carbon, nitrogen, oxygen, fluorine, neon, any of those. They all would give you an mark. Any one of them. Isn't that great? Complete the sentence by putting a cross in the box next to your answer. So the relative charge. Aha! Right, so we've gone from masses to charges. Electrons. Do you remember? Neutrons are neutral. Protons are positive. P for proton, P for positive. So we know that the 0 is a neutron. It's -1 or -2. When an electron's not -2, it's -1. I'm stalling for time, let's be honest. Electron's -1 charge. Everybody knows that. And if you don't, learn it. The electronic configuration of phosphorus is 2, 8, 5. Remember, the 2 is the first shell, 8 is the next shell, 5 is the outer shell. It tells you you've got 3 shells. It explains in terms of electronic configuration why phosphorus is in group 5 of the periodic table, with 5 in its outer shell. Let's see how I can explain this one in a really slow way. So 2 is in the first shell. First shell holds 2 maximum. 8 is the next shell. That holds 8. And then you've got 5 in the outermost shell, and the number of electrons in the outermost shell gives you its group number. So I probably would say phosphorus has got 5 electrons in its outermost shell of electrons. That's what I would probably say. And then you get 2 marks, because you say it's got 5 electrons in the outer shell. Good. Question 3. The table shows the number of electrons, neutrons and protons in particles P, Q, R, S, T and V. So we have particle P, Q, R, S, T and V, and they've taken the symbols away. How naughty. So you have to use your periodic table to work it out, but there's many ways you could do it. I could think of maybe 2 or 3 when I was writing the answer to this question, and I went, oh, hang on a second. It's a cheeky question because it says they could ask about ions here. So actually the table's quite cleverly designed. We've got an ion, and it says it's negatively charged. That means it's got more electrons than it does protons, because if you recall from the earlier question, electrons carry a negative charge. So to make an ion or an atom into an ion, you have to give it more electrons. Let's look down the table. Same number, same number, same number, same number. Oh, hang on. 18, 16. Look. T has got 18, whereas the other one is 18 and 20. That would be positive. But T is negative. V is positive, but T is negative because it's got more electrons than it does protons. The answer's T. More electrons than protons. Which particle are atoms? Careful, atoms of metals, not ions of metals. The previous question gave you a hint there. Ions of metal, ions, atoms. And it has to be metals. So let's look at what we've got at periodic table. Now we've got the protons, and if you look at the periodic table, it says the proton number is the bottom number. So all I have to do is look at the protons, and I can work out which one is which. One proton must be hydrogen. Then that one's got 3 protons, so that is lithium. That's got 8 protons. Let's look at that. That's oxygen. That's got 13. Let's look for the number 13. Aluminium. So that one must be aluminium. Oh, that's a metal, isn't it? Aluminium. And then silicon, sulfur. Okay, and that one is calcium. But it's got 18 electrons and only 20 protons, so that's actually an ion. So I know that lithium and aluminium are metal atoms. Calcium is a metal, but it's an ion because it's got 18 electrons, so it doesn't count. So it's a trick. If you got V, it tricked you because it's an ion. It wanted metal atoms, and so Q and S. Yes, aluminium and lithium. Well done. Tough question, that one. Very tricky, very cleverly worded. Each element has an atomic number. State what's meant by atomic number. What am I doing there? I'm having a talk about it to myself. I'm just double checking my working because calcium, you know. And I went, yeah, no, hang on. It's got 18 and 20 and it wanted atoms. Yeah, that's very clever. Yeah, I was justifying that to myself as a 2+ ion. Well done past me for spotting that. Clever me. Each element, and I'm probably making a little note to myself that that's the wrong one. Yeah. Each element has an atomic number. Each element has an atomic number. State what is meant by, that means definition time. If you got state what is meant by, it's a definition. It is atomic number. So we just have to come up with the definition of atomic number. What's the definition of an atomic number? The atomic number, I think this is on the periodic table actually, on the top in that box, isn't it? Is the number of protons in an element or in the nucleus of an element. But it relates to the number of protons. Now, we can change the number of electrons by making them into ions and things. But in the nucleus of an atom, we don't play with that in chemistry. It is the protons. And that's what defines an element to have its elementness. And it is, yeah, look, it's in the periodic table. It even tells you the definition's sort of clued in. Part 2, the atomic number of boron is 5, and then we're talking about isotopes. So we've got boron 10, which means it's got a mass number, that isotope's got a mass number of 10. And then we've got boron 11, and it says use this information. So you've got to talk about having different numbers of neutrons, because we know that the atomic number 5 is the number of protons, but the number of neutrons changes from 5 and 6, because 5 plus 5 is 10 and 5 plus 6 is 11. So we need to talk about that. What's the definition of an isotope? Same number of protons, same number of electrons if you wanted to add that in, but that's not necessarily where we wanted to go. But same number of protons, but a different number of neutrons in the nucleus. It's a definition again. What is meant by this, or use the information, is also a lovely one, because it gives you the answer and you just have to describe what you see. But they both contain the same number of protons, which is 5, but they have a different number of neutrons. Easy peasy. Oh, I'm writing something else. What else did I say? Oh, I added some detail. Look, I did some maths to prove it. I did 10 minus 5 equals 5 neutrons, and 11 minus 6. No, 11 minus 5 is 6 neutrons. There, that's what I did. So that's me writing that there. Then it says, explain what is meant by the term relative atomic mass. What is meant by the term? Another definition. Great. Relative means you're comparing it to something else. And this is in your revision, your Seneca revision, and a definition in the book. It's one of these definitions that I recommend you learn. The average mean mass of an element. And it's the mean mass because you're taking into account all of the isotopes in it as well. But but it's an atomic mass, so not necessarily. The average mean mass of an element compared to 1/12 of the mass of an atom of carbon-12. So actually, it's a very nice definition to remember. The relative mean mass of an element compared to 1/12 of the mass of an atom of carbon-12. Because otherwise, they'd look relative isotopic mass, and we're looking at the averaging all of the isotopes. I digress. Let's go back to this. We've got boron here as an example in your question, and it gives us the percentage of boron 10 and the percentage of boron 11. They're isotopes. They've got the same number of protons in the nucleus, remember, and we have to remember this equation. It's mass times abundance plus mass times abundance. You can do that as many times as you want, depending on how many they give you. They've given us 2 here, 19.7%, and the rest is boron 11. But yes, it's mass times abundance and mass times abundance. So we've got 10 times 19.7 and 11 times 80.3 divided by 100. I'm just going to tap that into the calculator. Tap, 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 tap. Put some maths down there. I could have put the calculator on the screen, actually. That would have been easier, wouldn't it? Gives us an average mass, a weighted average mass, because that's what it does, is it weights it according to the proportions of 19.7% and 80.3%, and it gives you the answer. 10.8%. Sorry, 10.8. This is lovely because it's rare to get such a straightforward question that gives you so many marks, in my opinion. I love the history questions. Dmitry Mendeleev produced the first version of the periodic table. Describe, so really story time, how he arranged the elements in the first version of the periodic table and why the elements are arranged differently in the modern periodic table. Tip of the hat to that would be handy for your 3rd mark. So what did he do? Think about what he did. He was an avid card player. He liked to spot patterns in things. He was a bit of an obsessive over this, and once he got into it, he spotted a pattern, and he used the properties of the elements that he knew at the time, and he put them in groups. So he's like, this all sort of behave in a similar way, so they might have similar properties. But he did it with mass numbers. At the time, isotopes wasn't known, wasn't well understood, and so he couldn't have done it that way. But he was so confident in his pattern spotting that he left gaps. So he used the properties of the known elements and their compounds, because sometimes the compounds would have similar properties at the time, and he arranged them by mass number. And he left gaps for ones that he predicted based on the properties that he thought would have. And he was so confident he could even say what the next element to be discovered in that gap would be like, which is really clever. But it's purely following a pattern. But nobody thought of doing it until Dmitry Mendeleev thought of it. And then he arranged them in order of atomic mass, because we hadn't done the isotopes. Nowadays, So how is it different nowadays? Well, nowadays we know about isotopes, don't we? And we know about mass number there. Atomic number is different to mass number. And it's the atomic number, the number of protons in the nucleus, that gives the element its properties. The elementness of that element is defined by the number of protons in that nucleus. And so that's how we do it now, due to the discovery of these isotopes. So lots of marks, it's about 3 marks. There's lots of points that would give you the marks in that answer there. He's the properties of the known elements and looked for left gaps, and we discovered isotopes. There's lots in that answer. The element beryllium, magnesium, calcium. Oh look, they're all in the same group. Interesting. Beryllium, magnesium, calcium, strontium and barium are in group 2 of the periodic table. Each calcium atom contains 20 electrons. Which is the correct electronic configuration for calcium? They can only ask you up to calcium, the first 20. They're only going to ask you calcium. This is the biggest one that you're going to get. We know that the first shell of electron holds 2 electrons. The second shell of electrons holds a maximum of 8 electrons. The third shell of electrons holds a maximum of 8 electrons, and so on. Right, so we know that rule about electron shells filling. And we can't break that rule. So 2, 8 and 10 breaks that rule. It can't be that. 2, 8, 8, 2. 2888, 2288, that can't be right. 2102, that can't be right. In fact, the only answer without any working out has to be B. And we also know it's because it's in group 2. It's got 2 electrons in the outer shell. So going down, we only really had B and D to consider, and D breaks the octet rule because it's more than 8 in the second shell. So yeah, that's not the right answer. It's got to be B. So yeah. Many ways of describing why that's wrong, but learn those electron shell filling rules because they're really handy, and they could ask you for the electronic configuration of any of the first 20 elements, and you could work it out by counting along and working out how many electrons are in the outermost shell. The periods give you how many shells, the groups give you the number of electrons in the outermost shell. Yeah. Question number 6. Calcium oxide is an ionic solid. Ionic, metal and non-metal. That's what it is. Figure 5, we've got, what do we got? It shows the electrons in calcium atom and oxygen atom. Notice the 2 outer electrons in calcium. Interesting. It's a metal. Metals like to lose. Metal likes to become positively charged. So, note that. And then oxygen is in group 6, and it's got 6 electrons in the outer shell. Interesting. It needs to gain 2. It's in group 6, 6 electrons in the outer shell. Calcium's in group 2, and it has 2 electrons in the outer shell. There we are. Complete figure 6 to show the electronic configuration and charges of the calcium ion, means it's lost or gained electrons. It's a metal, so it's going to have lost. And the oxide ion. Use dots for the electrons originally on the calcium, and crosses to show electrons originally on the oxygen atom. So there's your dots, and it wants you to show what's moved across to where. The calcium, spoilers, is going to give its electrons to the oxygen. Oxygen is going to fill its outer shell by gaining 2 more electrons to give it 8 in its outer shell. That's going to give it an overall -2 charge. There's the 2 electrons from the calcium going on. There's the remaining 6 that were drawn previously, giving a full outer shell of electrons there. And the outer shell is now empty, but notice that they've not finished this shell. So I'm going to finish this shell here with the dots. Cheeky. So the outermost shell is now gone, and it's now a complete shell because that shell has got 8 electrons as well. 2 plus charge, if you wanted to represent it with square brackets, that's common, and the 2 minus charge. But it says the charge on the ion, you can say +2 or 2 plus. Charge on the ion is -2 or 2 minus. Both are allowed in the mark scheme. So a mark for that, a mark for the electronic configurations. So that's how you get your 3 marks from that. Arguably, I suppose it could be 4. I don't know. But they're giving you 3. That's what we're going to go with. I'm sure they've got a good reason. Sodium chloride is an ionic compound because it's sodium and chlorine, metal and non-metal, with a melting point of 801 degrees Celsius. This was a killer question. Explain why the melting point of sodium chloride is high. We know electrostatic attraction between oppositely charged ions is an ionic bond. We've got a 2 minus and a 2 plus in the calcium oxide just now. This one is a +1 and a -1 from the sodium and the chloride, and they're strong. It's a strong electrostatic attraction. in between the ions in this giant lattice, and it takes a huge amount of energy to melt it, because we've got to overcome those forces of attraction. We've got to pull those ions apart, and actually that's the answer. It's very strong attraction. It's very strong ionic bonds. It's very strong electrostatic attraction between oppositely charged ions, and it requires a lot of energy to separate them. That's the answer. If you said intermolecular, it's wrong, and you automatically scored 0, because if you say molecular, you're talking about simple covalent, and you automatically forfeited your mark. It's such a shame, even if you got one of the points correct. I know, cruel, but that's what they did. So electrostatic attraction between oppositely charged ions requires a lot of energy to overcome those strong forces. Magnesium. Magnesium has an electronic configuration of 2, 8, 2. Remember, first shell, second shell, third shell. The first shell holds 2, next shell holds 8, and on the outer shell you got 2. Oxygen's electronic configuration of 2, 6. Well, we know that. We've just done a question on that, so that's helpful. It's always nice when they self-reference their questions, so you might not get that in the actual exam in GCSE, but in these mocks and in these CTs you will get that, because there's only a certain number of questions we've got access to. Explain in terms of their electronic configuration how magnesium-oxygen atoms form the compound magnesium oxide, and a description of the structure. It's an ionic, so it's going to be a lattice. So we already know it's going to be a lattice, so we'll just put a lattice in there to remind me to talk about that. We've just had it with calcium oxide on the previous page. We did it diagrammatically. We did it with a diagram, and now we've got to explain it with our words. You can do this in bullet points, and you can actually draw your answer. What do they say? A picture paints 1,000 words, or something like that. A picture's worth 1,000 words. It's great. It's a great way of doing it. So if you know your square brackets and your transfers and all that, draw it. The examiner will understand it. Add labels to your drawings. The examiner will understand it. Use bullet points. All you're trying to do is get across this description that magnesium atoms want to lose electrons. They're in group 2, so they've got 2 electrons in the outer shell. And because it's got 2 electrons in the outer shell, it wants to donate them. We're looking at a non-metal, so it's going to donate to a non-metal, which is going to receive the electrons. By donating those 2 electrons, it's going to give it an overall positive charge, because it's lost those negative electrons, and it's lost 2 negative electrons, giving it an overall 2 positive charge. Losing those 2 minus electrons away, get rid of those 2 negatives, leaving the protons in the middle, outbalancing those electrons, giving an overall Mg2 plus charge, because it's lost those electrons. The electrons are transferred across, and they go to the oxygen, because we're making an oxide, which is really lovely. So that completes its outer shell as well. Happy oxygen. That's energetically more stable, and we end up giving the electrons, which are negative, to the oxygen, making it into an oxide ion. So the oxide ion is negative by 2. We need to state that. So we've got 6 electrons in the outer shell. It wants to gain 2 more electrons to make 8 to get a complete outer shell. By gaining those 2 negative electrons, it gains an overall charge of 2 negative, 2 minus. So it forms an O2 minus, or oxide ion. Hope that makes sense. So we get 2 from the magnesium, which is in group 2, 2 plus. Our oxide gaining 2 becomes 2 minus. Remember, electrons carry negative charge. Now that completes the outer shell of oxide, and completes the outer shell of magnesium, because it's got rid of its outer electrons, going to the next shell in, and that shell is full automatically, because they fill up from the inside outwards. The positive magnesium 2 plus ions, because the 2 positives, opposites attract the negative 2 minus ions. That's how you build up your lattice, isn't it? So you see how I've led the reader into understanding how the opposite charges attract, and it forms a giant ionic lattice. I think I'm about to write that, when they come together and attract, forming the ionic bonds. Electrostatic attraction between oppositely charged ions. The ions pack together to form a giant ionic lattice. What a lot of marks I could get for that answer. Many, many marks. I'm having a think. What am I thinking? Oh, I'm saying this is, that's what I was saying. Bullet points are good. Diagrams are good. I wonder what I was writing there. Diagrams are good. Bullet points are good. Yes, anything that gets those points across. Remember, it's on the previous page. You can look at what the diagram would look like, and you can rewind this video a bit if you want to know what the diagram would look like. With calcium, you've got more shells. the same principles there, though. Look at the number of marks that are available for all of those things that I've written. You only want 6, and I've got many, which is an easy load of 6 marks. That 6 marker was an absolute dream. Hope you get that in your GCSE. The formula of aluminium nitrate, has oxygen in it, is Al bracket NO3 bracket 3. How many atoms? Let's work it out. We've got aluminium, we've got nitrogens, we've got 3 of anything inside the bracket, so 3 nitrogens. Okay. 3 O3s, so 3 lots of O3, which is 3 times 3, 9. 1 plus 3 plus 9 is 13, so I've got 13 atoms. Yeah. 3 of anything inside the bracket. That's the way that works. What's the most likely formula of aluminium nitride? Ide versus 8. If you've got 8, you've got oxygen there. So anything with 8 usually has got oxygen. So it's not that one. It's not that one. It's not that one. That doesn't have an oxygen, so it must be an ide. Easy peasy, lemon squeezy. Yeah, not too difficult. Covalent bonding by the look of it. What have we got? Question 9. Hydrogen sulfide, H2S, is a simple molecular covalent compound. A hydrogen atom has 1 electron in the outer shell. Okay, it's going to need 1 more because hydrogen's in period 1. And period 1 is first shell. First shell holds 2 electrons. See what I did there? It needs 2 electrons, so it only has 1. So it needs to find 1 more from somewhere, probably by sharing it. A sulfur atom has 6 electrons in the outer shell. So it needs 2 more. So if it's in period, I don't know what period it is. It's in group 6, so it's got 6 electrons. It needs to get to 8. And how are we going to do that? Well, it needs 2. So hydrogen needs 1. It's H2S, so you don't even have to work out the formula. It's telling you how many hydrogens. Let's complete these shells and have a look. So this first one is wrong, because the hydrogen on the left is fine, but the one in the middle has got 4 electrons, and it only wanted 2. This one has got 6 and 2 and 6. Oh, it's that one. Let me show you why this one's wrong. Complete that one, not enough. That one's fine. That one's not enough. So those two haven't got enough electrons in their outer shell. Look at the diagram. This one has 1, 2, 3. Oh dear, that's not right. That's got 1, 2, 3, 4, 5, 6. That's not right. And that one's got 2. So the sulfurs hasn't got enough, and that hydrogen is, yeah, that just doesn't work. That's just too many for each hydrogen on the left and right. The only correct answer is B, because we wanted full outer shells. This one, which row in figure 6 and its row going across shows the properties of simple molecular covalent compounds. So remember, simple molecular, you've got weak intermolecular forces. You don't have charge carriers because the electrons that carry charge, they are occupied and not available to flow. So we're expecting something with a low melting point, a low boiling point, and a poor conductor. And there's only one that fits that, and it's C. So C's the answer. And that's that. There we go. Okay, so let's look at this question. It's about nitrogen and oxygen being present in the air. Complete the sentence by putting a cross in the box next to your answer. Oxygen has a low boiling point because it's simple molecular. So what do we want to talk about? We want to talk about intermolecular forces, don't we? And those intermolecular forces are going to be weak, and that makes them easy to separate. So what's the question? Weak covalent bonds between the oxygen atoms. Well, that's a misnomer, because you can't have a weak covalent bond between them. It won't work like that. Weak covalent bonds between the oxygen molecules. No. Now, weak force of attraction between the oxygen atoms, or weak force of attraction between the oxygen molecules. Yeah, they nearly got you with that one. That's a tricky one, but D is the correct answer. Weak force of attraction between the oxygen molecules. Another gas present in the air is carbon dioxide. Look at that. There are covalent bonds between the atoms in a molecule of carbon dioxide. And what is meant by? What is meant by? Definition time. How many marks? Gosh, lots of marks from definitions. Learn your definitions. It's very easy to do, and it's easy marks in a test. So a covalent bond is defined as a shared pair of electrons. If you get that far, you pretty much get all of the marks. A shared pair of electrons between two atoms. It's such an easy definition, and I love it. So you get 2 marks for it. It's great. The electronic configuration of oxygen, atomic number 8, 2 in the first shell, 6 in the next shell, 2 plus 6 is 8, is 2, 6. Give the electronic configuration of carbon, which is in group 4. So it's in period 2, so we know we've got 2 electrons, shells, and it is in group 4. So, and it's got an atomic number of 6. 2 ways of working it out. You could do 2 in the first shell, 4 in the second shell, 2 plus 4 is 6. Or you could work it out from period 2, you got 2 shells, 2 in the first shell, 4 in the outer shell because it's in group 4. Both methods work. Bottom line is 2, 4. 2 in the first shell, 4 in the second shell. Next cell says, killer question. Draw a dot and cross diagram of this. Carbon is in group 4, you've just worked it out. And then you've got oxygen, which is in group 6, and we've got 6 electrons in the outer shell. How are we going to do this? Have a think. This is actually quite an easy one to remember. I recommend remembering this one because it's surprisingly common. So we've got 2 more to get for the oxygen, because 6 to get to 8 is just 2. But carbon needs to get 4 more to get to 8. So the way it does it is by sharing 2 pairs. So it's called a double bond. It's called a double bond. So carbon will form 2 bonds to the left and 2 bonds to the right in this diagram. It only wants you to draw the outer shells, which is nice. So you draw your carbon and your oxygen. So you do carbon bringing in the 4 electrons that it's going to share, and then the oxygen dots, 2 pairs shared there, 1, 2, 3, 4, 5, 6, 7, 8. Carbon's happy, so carbon works. I say happy, I mean energetically more stable, but you know. And then the oxygen's got 6 electrons in the outer shell, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, giving you a total of 2 more from carbon. 1, 2, 3, 4, 5, 6, 7, 8. And on the other one, 1, 2, 3, 4, 5, 6, 7, 8. Pause the video if you need to, but there you will see that both have got 8 electrons in the outer shell as well, meaning carbon and oxygen are satisfied. That's a covalent bond. That's your dot and cross diagram for a molecule. And that, everybody, is the end of the paper. How did you do? Write your answers down. Congratulations, you are done.
Got the textbook open wide now, nowhere left for me to hide now. Trying to learn about the elements, all the facts are feeling relevant. Mr. Marsh is on the whiteboard, giving us the knowledge we need for it. Oh, getting ready for the test, putting all our skills up to the best. Chemistry is gonna be a breeze.